Which clock is this set on? Okay, so last time we did the DG schemes. I think we did discuss about DG manifolds. So, so just to remind you, definition was a DG scheme M is it's called smooth or a DG manifold if one, this we wrote last time. So if one M0, the regular underlying scheme of this thing is a smooth algebraic variety, and two, that somehow locally on Zariski topology of M0, this thing can be given as, so we have an isomorphism. We have an isomorphism of the DG algebra of our space. Well, of course, the graded sheaf given by the DG, induced by the DG algebra of space to be the symmetric algebra over all M0 modules of Q minus 1, Q minus 2, and so on, where QI's are vector bundles. So they are vector bundles on M0. So, of course, every manifold has this property. The fact that these are vector bundles actually gives you the smoothness and the following way. So, for instance, and then we define this notion of the dimension. So we defined dimension of this smooth DG scheme to be a tuple di of m I greater than or equal to 0, where d0 of m was the dimension of m0, the regular scheme, and di of m were defined by the rank of these bundles. Okay, so that is what the dimension is. And now there is a cotangent sheaf, so the cotangent DG sheaf of M is defined as in the usual sense is defined as in the commutative case as the target of the universal derivation morphism, universal derivation, which is just a map from the DG algebra of the DG scheme to the sheaf of first order differentials of the DG scheme. And we know what these are. I mean, we know exactly what this is, and we know exactly how to define this thing. There are many ways of constructing this. Well, there is, you can take this and, for instance, in the regular, it's a level-wise construction. So in the level of the regular scheme, you can take the scheme embedded inside this diagonal, right? And then the conormal sheaf of this embedding basically gives you this. And then you can keep doing the DG cotangent sheaf. And so this is the universal one for all levels, but this construction is level-wise. Obviously, this has a differential and this has compatible differentials. Remember that when we're doing the construction of the derived stacks, higher derived stacks, we already did it over the category of simplicial commutative rings. We already did this construction. So it's that. And then proposition omega 1 dot of M, the DG sheaf, is Z graded coherent sheaf. Coherent sheaf, which is Z graded coherent sheaf, which is a vector bundle. Vector bundle of rank Ri di of M. So it's a filtered object, like that. Now, similar to the cotangent, DG cotangent sheaf, we have the DG tangent sheaf, which obviously is given by the dual of this. The cotangent sheaf is given as the target of this universal derivation. So if I want to construct the DG cotangent tangent sheaf, I need to take basically a map from here to O dot of M, back to O dot of M, so dualize it, right? So I need to compose the map. So then we have the, so let's see, we have the DG tangent sheaf T dot of M defined as T dot of M is given by derivations over our underlying field O dot of M back to O dot of M, and this is really the composition. You can see that, and so which is the same as homomorphisms over the ring of O dot M over the algebra of O dot M modules from omega 1 dot M back to O dot M. But of course, this sheaf is given by this morphism, so you can see how it's given. So this is a quasi-coherent sheaf of PGD algebras, and it's differential, and it's differential is given by the commutator with the differential of O dot. Differential is given by, you need to work it out. I leave that as an exercise or practice to see it. So differential is given by a commutator with differential in some, maybe you can also see it in some literature. It is coherent. This is quasi-coherent, but it will be coherent. It is coherent if and only if di of M is equal to 0 for I bigger than equal to 0. Yeah. Much larger. And further, if X is a point in here, is a K point of this DG manifold N. So what is this? What does this mean? This means the pi 0 of M over the field, right? Underlying, we know what this is, right? So we know exactly what this is. So we looked at the DG algebra of M. It's a graded thing, and we took the zeroth cohomology of it. And we know that it embeds, as a space, it embeds inside the regular scheme, underlying the scheme of M. Right? So you know, you have this thing, and you have this thing, and this goes inside here, because even this one, the structure ring of this will be, this is given by the module, zeroth cohomology module, and it will be, that module is a module over O of M0. So you have an injection factor. So, okay, but a K point of M is given like that, and as the fiber of this over K, so this is a K point. The K point, the tangent DG space, to M at X is defined by the DG tangent sheaf, the fiber of the DG tangent sheaf over that point, which is all the derivations now over K, because now we have restricted to K. So, and from O dot of M to K of X. And what is this? This is really just nothing but T dot of M tensored over O dot of M K of X. The function field at that point. And well, this is same way that we can define tangent space to a regular scheme, right? So we look at the fiber of the tangent sheaf on that point. So here, where K of X is the one-dimensional O dot of M DG module corresponding to X. Skyscraper sheaf, if you like, the DG skyscraper sheaf, at that point. Moreover, we can define tangent to space, tangent space at a K prime point of pi 0 of M, where K inside K prime is a field extension. Well, this is highly important when we do deformation theory on moduli spaces. You have moduli space of objects, and you have this moduli functor, and often you pick some parameterizing scheme, and you look at the fiber of the moduli functor over that parameterizing scheme. It gives you a flat family over that parameterizing scheme on your origin of the space. Okay, and then you extend the scheme. Parameterizing the scheme, to extend it like a square zero extension or something. In the level of points, though, this is similar thing. If your parameterizing scheme is just a point, geometric point, you can still extend it by the field extensions. And then you can discuss whether you can define this thing. So this is a field extension. We will sometimes use the notation I of M centered at X as the cohomology h minus 1 of the h minus I of the t dot of x at n tangent sheaf. So now we know what's the pi 0 of m. Now we know what is the higher homotopy groups. Higher tangent. Actually, higher. Okay, so it's defined this way. This is just a notation. Okay, so that's that. Now, there is something I can say in here. And before the class starts, this is actually something I was trying to work out, but I don't see precisely the reason yet. So maybe we put it in here and then we think about it together. So more to say on this. Let K prime be an extension of K, and let an X be an K prime point of M. Point of M. Then any choice of a formal neighborhood or formal coordinate system on M near X. That basically means you look at the formal ring and the formal neighborhood of X gives rise to a structure of a homotopy Lie algebra. This I will tell you what this sentence is. On the shifted, this is the part I haven't seen myself yet. On the shifted tangent TG space, more or less maybe, I don't know why. The shifted tangent DG space, T dot of x of m shifted by -1. Yeah, no, but I think this argument of the kernel and the shift maybe works. Okay, so in particular, now let me spell it out. In particular, at the level of cohomology, we have well-defined Whitehead products. What are those things? So what does that mean is the following. It is something like this. It's the Lie algebra. It's the thing that defines the Lie algebra structure on this tangent sheaf. I mean, fiber of the DG sheaf of DG tangent sheaf at every point. So the Lie algebra structure takes you from here K ij in here to I plus j minus 1. And these are exactly defined as before. For instance, in the j part. Okay, and making I dot plus 1 into a graded V algebra. I think naively I can see that y choice of a formal neighborhood or the formal ring around the x gives you the shifted tangent complex. You need to kind of work it out. Yeah, but if you figure out why the shift, tell me. So again, let me spell it out even further. So more precisely, what is this trying to say?
Oh, I think I might know. It's because because co-commutative algebra, when you take the dual operator, it's least shifted by -1. Like I think that.
But can you see it? Concretely? Can you see it using the regular scheme, the analysis I put there? I take my scheme, I look at a point in my scheme, and I look at the formal ring around that point. So you have the scheme, you have the point, this is the maximal ideal around here. So now completion of this around this is what? Is basically this limit. Like that. On the other hand, the cotangent space at that point, at this formal neighborhood, the cotangent space, well, the first order space, the second order space, and all of that is given by the following. So well, you always have this exact sequence. Somehow from here, and this thing is the conormal sheaf. This is the cotangent space. For higher, for n equal to 1, this gives you literally the cotangent space. Conormal sheaf of x inside n. And for higher and higher n gives you higher cotangent spaces. So take that as your model and take the inverse limit of all of those exact sequences and then connect them to each other via these differentials. So probably somewhere, when the way I see it, but I cannot justify it, is that these two things in the limit approach to one another, and inside the category, in the DG category, this thing becomes isomorphic to that thing. What would be the shift? I cannot see it precisely. So if you can figure it out, please let me know.
So you're saying something on the line.
Oh, or the dual. In the dual.
Yeah, but okay, so.
But I cannot see it.
I mean, in very vague sense, what you're saying is that you get
Yeah, in very vague sense, I'm saying these two things are actually convergent to one
zero,
another.
so you get the thing.
Yeah,
that should be shifted to the left.
That's
or I'm not sure how to see it from here, but intuitively it's clear. It's just there's that reason. There's the opera dual is shifted one. There's also I think in general, if you want to take the functions over a formal neighborhood, which is like the dual to the universal developing algebra. What you do is you need to take a loop of the algebra of the two.
Taking a loop, shift.
Yeah, so you take a loop, you shift it by 1, then you take the dual, you shift by -1. So
why do you take the loop? So what the question is, do you have some regular, for the algebraic geometry, do you have some way of seeing this without, why do you take the loop? Okay.
All right, let me think a little bit on that.
Yeah. But for me, because I'm a geometer, I would like to reason it this way, but I cannot do it. Because I tried a little bit, I didn't have time to. Anyways, but more precisely, if we have some graded vector space, if this guy is a graded vector space. And then we have the completed dot hat, for instance, symmetric algebra of the dual of this graded vector space shifted by -1, and its derivation D satisfying D squared equal to 0. The problem here is that I don't have an intuition, geometric intuition of this shift. That's the problem. Satisfying D equal to 0. And basically this thing serves as the cochain complex for this guy. Oh, so now here we take G dot to be this thing. And the completed local ring with its natural differential serves as cochain complex for G dot. Yeah, so a choice of formal coordinate system identifies it with this guy. My guess is again that it needs to be seen somehow that way, but honestly, I don't see why. I tried to reason with check covers and things like that. I couldn't. All right, but have a look at the paper of Kapranov and Silvan Fontaine on this thing, and if you figure it out, let me know. Okay, so now any morphism F from M to N of EG manifolds induces a morphism of cotangent coherent DG sheaves. So coherent, but these are going to be cotangent DG sheaves. Coherent DG sheaves, which are is, if you have a morphism like F, then the star of F is going to be mapping from back of DG cotangent sheaf of N to DG cotangent sheaf of N. And for any X in M over K, which is pi 0 of M evaluated at K prime, X in M of K prime, a morphism in homomorphism of complexes fits into a morphism of quasi-coherent DG sheets, which is d of f going from t dot of m to f star of t dot of n. Well, this is the dual to that one. Okay. Remember that these are DG cotangent sheets. So for regular scheme, it's just fibrant, cofibrant object. And remember that when we were constructing these derived stacks over the calculus of simplicial rings, we had the cotangent sheet, but then the derived object, that the cofibrant model of that thing became actually the cotangent complex. So again, as a characteristic of the DG world is that even the cotangent sheet itself is some kind of a graded object with the differentials. So on top of this, you can construct for non-smooth DG schemes the cotangent complex of these things. So it will be a bigraded complex. And this we will discuss. Okay, so proposition, I do not prove it, so let f from m to n be a morphism of DG manifolds. Then the following conditions are equivalent. One is that f is a quasi-isomorphism Okay, so we need to remind ourselves what does the quasi-isomorphism of the schemes mean, right? So if I have a morphism of two DG schemes, we know that there are two graded structures that I can associate to the DG scheme. So one of them was that I could have, okay, so one of them is the regular scheme together with this guy, where I just delete the differentials. That was one of them. So that's a graded algebra with differentials, trivial differentials, and the other one was pi 0 of m with this guy. And because the cohomologies have trivial maps between them, this is also a graded scheme associated with this DG scheme. So, in particular, a morphism between two schemes is called quasi-isomorphism if in this level you have isomorphism between the corresponding graded schemes. So you would like to have something like this. So for this one. So that is that. But if that is the case, then the morphism of schemes pi 0 of f, which takes us from pi 0 of m to pi 0 of n, is an isomorphism. It's an isomorphism. Well, yes, and for any field extension k in k prime, we have that, and any k point x of m, k point x of m, the differential of f, the differential dx f induces an isomorphism pi I mx to pi I n f of x. Okay, so it's very much the DG version of the diffeomorphism. And part 3 is that pi 0 of f is an isomorphism, and this map that we just defined, which is from here to here, is a quasi-isomorphism of coherent DG sheaves. Okay, and then moreover, if any of these conditions are satisfied, if any of conditions 1 to 3 are satisfied, then df t dot of m to pullback f star of t dot of n is a quasi-isomorphism. And by this, we really mean the quasi-isomorphism of DG sheaves. Again, because we are in the DG world, even between sheaves, we have the notion of quasi-isomorphism. And this we discussed before. If I have a sheaf of O dot M modules on a DG scheme and a morphism between two such sheaves, then quasi-isomorphism again means isomorphism in the level of the graded sheaf that you can associate by taking the cohomology over the O0M modules. So that's that. Now that, the proof of this thing for the proof Kapradov content. There are some lemmas and so on that we need. I think that since this is somehow exposition, so you can find it there. Okay, why are we doing this thing? We are interested in DG manifolds and their morphisms because later we would like to work for all DG schemes. We would like to resolve our DG schemes with the smooth DG schemes. This is why we are trying to do it. Like for instance, as I told you, we have the notion of intersection of the schemes. We have the notion of derived intersection of the schemes. Whatever derived intersection means, it means that take a scheme and replace it with its smooth resolution, and then use that to define the intersection. So this is where we are going. Okay, so let us discuss that. Existence of smooth resolutions. So, homomorphism of DG schemes schemes. F from X to Y will be called closed embedding. Will be called a closed embedding if F0 or F0 from underlying the scheme of X to underlying the scheme of Y is a closed embedding. It's a closed embedding of the schemes, and the structure morphism of sheaves of DG algebras. What is that? That is F0 upper star of O dot of N to O dot of M. These are all O0 X, X, Y, so Y and X. These are all O0 of Y and O0 of X modules. So quasi-coherent sheaves of O0 Y and O0 X is certain. And so now you have the closed embedding. Now there is a theorem so for any quasi-projective DG scheme, so that this was something, if you remember, this was the thing that its underlying the scheme is quasi-projective and its structure algebra is bounded above. So for any quasi-projective DG scheme, X, there is a DG manifold M and a quasi-projective and a quasi-isomorphism, quasi-isomorphic embedding, closed embedding. So there is an embedding of this thing into an ambient DG manifold, where isomorphism of DG schemes is quasi-isomorphic. Part B of the theorem is that given any two embeddings, let's say X goes to M and X also goes to N, as in A, they may be complemented by a quasi-isomorphic closed embedding, by quasi-isomorphic closed embeddings. Let's say M goes to some other guy L, and N also goes to that guy L, such that you get the natural commutative square of embeddings. So that this commutes. Okay. So the proof is, what is the, okay, so we have half an hour. Proof. For instance, part A implies B, so given M and N, that we can just define this Y to be M union over X. Okay, which it means really regular scheme of N and union regular scheme of N over X and O dot of N. And so over O dot of X. O dot of N. And then we will have, then we get what it is. So this is okay. This is okay on that, except Y may not be smooth. May not be smooth. In which case, we need to embed Y inside something, into something smooth. Embed Y into a DG manifold L as an A, which we can do with assumption. So how do we do it? Essentially, claim is that if it is affine, it is pretty doable. So, and then if it is more general, like quasi-projective, then you need to kind of embed it inside some projective space and then do it locally. So that is actually the proof of part A. How do you actually do this embedding? So claim is that if you assume A, then you can always do this. Now, how do we do that? Right? So if so let's see. When X is affine, this is a consequence of the F that for a degraded DG algebra, we have a free resolution. Okay, you can see where it goes, right? Because the DG manifold is the one that this regular scheme is smooth, and then it's the structural algebra is given by symmetric algebra, a bunch of vector bundles. If you have the structural algebra of the scheme, and the scheme is affine, it always have this resolution by the vector bundles. So from the resolution itself, you can just embed it inside something smooth. So if this affine is fine, then the claim affine is okay. So that's that. For the more general case, that X be X0 in a structural algebra, be given as x0 is a quasi-projective scheme. Projective scheme, we can choose an embedding. Of it into Pn as a locally closed subscheme. Now take M0 to be an open subset. N such that x0 is closed in M0. If you pick n large enough, you can always do it. Then construct O dot of M by induction. As the union of sheaves of PG algebras, where O dot O of M0 is just O dot 0, and then it sits in O dot 1, and it keeps going like that, such that O dot I is obtained from, you need this symmetric algebra of the vector bundle. This is what exactly it is. O dot I is obtained from O dot I minus 1 by adding a vector bundle of generators in degree I. Well, you can see that even naively and intuitively this actually is true. So you're just cooking up this, this PG manifold. You're cooking it up. You embed your regular scheme x0 inside some projective space, and then in there you just take some open affine thing in there, such that x0 is closed in it, and then for that open affine thing, now you need to construct this PG algebra. And you need to do it via vector bundles, and that's what we actually do. So you thicken that thing a little bit, the structure ring of that thing, you thicken it in the PG direction, so this actually gives you what you want. Okay. And not only that, you also need further for this structured PG algebra, we need to further. We have further. We have a system of algebra morphisms. Morphisms EI from O dot I to O dot X, because of course you need to show that this this bundle, this symmetric algebra of the bundles that you're constructing surjects onto X. You need to say that your X is a closedly, it's going to be a closely embedded into this DG manifold, right? So you're constructing your DG manifold, and now you need to show that the structure algebra of the ambient DG manifold surject onto the one for X. So how do you do it? You look at pieces, and then you say that so that each pi is bijective in the J cohomology sheaf for J between minus I plus 1 and 0, and surjective on Hj for J less than 0 minus I. Sheaf of J cocycles, right? So, remark. This finishes the construction, but I will add a remark here that you also need a lemma that shows that if phi from C dot to D dot, two complexes, the quasi-isomorphism of complexes of vector spaces which is surjective on cocycles, which is surjective on cocycles, then phi from C dot I to D dot I is also surjection. It's surjective for all I. Anyways, after you prove this, by looking at the union of these things that you constructed, that gives you the structural algebra of the ambient DG manifold. And it surjects onto DG structural algebra of your X. So this is for the general case of quasi-projective. So if X is affine, you already have it. If not, you embed it inside something affine and you construct a suitable DG algebra. Okay. I think this you can see in the work of Barron, and also see in the many places, this construction. What time is it? So now, smooth morphisms. By the way, can you remind me in, let's say, 15 minutes? Because one thing we could do, we could finish earlier today and then go to the Science Center and Lazar from the Stony group is giving the talk. Yeah, let's do that. So we can enjoy that. Okay, so smooth morphisms. Let's just do another 10 minutes on it. So definition. Let M and N be DG schemes of finite type morphism F from M to N is called the smooth smooth if A, the underlying morphism F0 from M0 to N0 is a smooth. And B, locally on Zariski topology on M0, of M0, we have an isomorphism. We have an isomorphism of graded algebras. And that's the one you can guess. So we would like to have locally this graded algebra where we have deleted the differentials to be isomorphic to symmetric algebra over M0 of some module Q dot cancel with F0 upper star O N sharp. Well, again, here where Q dot is the sum of Qi is a graded vector bundle. For instance, in the case of a closed embedding into a DG manifold, we had that. I mean, in the case of a closed embedding into a DG manifold, those O dot I's could be used in here. Note that we have the relative cotangent DG sheaf, omega 1 dot M over N, which is a Z-graded vector bundle, and the relative tangent sheaf, tangent DG sheaf, okay, which is T dot of M over N is given by the derivations again over pullback of O dot N modules from O dot M to O dot M. Well, it's true, right? So the point is that if you have a smooth morphism, then the relative cotangent complex of this thing collapses to relative cotangent sheaf. And similarly, you can have the dual one, which is the relative tangent sheaf. And later we will do relative cotangent complexes of DG smooth. Or non-smooth DG smooth. And this thing is equal to, again, homomorphisms over this module, O dot M modules, omega dot 1, or omega 1 dot Mn to O dot of M. Remember again that, well, you know, if you have this morphism from M to N, principle, you will have this short exact sequence, omega 1 dot n goes to omega 1 dot m, and then you have omega 1 dot m over n. Everything is realized as a module, as these are sheaves, DG sheaves on n. So all of these things are, O dot m modules. In particular, the relative cotangent sheaf is also an O dot m module, and the relative tangent sheaf is given by the dual of that thing over the category of O dot m modules. So we have that. This is a quasi-coherent DG sheet. It's bound above with our notation. Okay, maybe 2 more minutes. So remark, if x from n to f is a section of f, so and x is this way, then so what does that mean? An endpoint of n DG scheme n, it's a scheme over n, so it's a DG scheme, n DG scheme. This is an n DG scheme, and I'm looking at an endpoint of this n DG scheme. Okay, so if that is x, then the tangent sheaf, produces the tangent DG space. So tangent DG space to m over n at x is given by, well, just a fiber, so it is t dot of x of m over n, which is pullback of the t dot via that point n over that. For the morphism x, you are looking at n over m, right? Which is the same thing as x upper star of t dot of n over m tensored with pullback of the O dot of m via that point x tensored with O dot of m. Again, it's very easy to see all of this. It's clear after staring at it. Again, this one is a quasi-coherent sheaf. Quasi-coherent sheaf on n. Okay, so what we are going to do is, now we have the morphisms, the smooth morphisms. We are going to basically go to, we're proceeding by saying that now we have the schemes, and we can define the notion of fiber product of DG schemes, but in particular we can look at the notion of derived fiber product of schemes. Now that we know every scheme can be embedded inside a DG manifold, right? Then we can define the derived fiber product by replacing one of our DG schemes with this resolution. Exactly how you look at the derived tensor product of sheaves. You replace that object with the resolution. And a direct and immediate application of this thing is in intersection theory. You have two schemes, and they are intersecting inside an ambient variety of two varieties, you can define a notion of derived intersection of these two fields. And now by this construction, you can actually see that the derived intersection sees all the infinitesimal properties of the actual locus of intersection. So you just look at the embeddings and you replace one of them with the resolution. This is how the flavor of derived geometry is going to be. Okay. I think this session was kind of fundamental things, but also extremely important. So I would like to emphasize that this embedding inside the DG manifold, that's basically the whole point. Can we do it for moduli schemes? That's the whole point. Okay.